Everyone, welcome to my channel. So in this video I'm going to cover the solution to this question called sum of distance in the tree. So before we start the real content for today, I would really appreciate that if you can help subscribe the channel because it can help this channel to grow. So thanks in advance. So let's start to do the real content. So in this video there are two goals. The first goal is to see how to solve this problem, and then we are going to do some live coding here. The second goal is to see how we should behave in a real coding interview. So let's get started. So the first step in the real coding interview is try to understand the question. If there's anything unclear, clarify with the interviewer, and also at the same time think about some edge cases. So let's take a look at the question. Sum of distance in the tree. So an undirected connected tree with n nodes labeled 0 to n-1, and n-1 edges are given. So the ith edge connects nodes edge I0 and edge I1 together. So return a list of the answer, where answer I is the sum of the distance between node I and all the other nodes. So let's see, for this example, we have this, the tree is something like this. So the distance to node 0 is 8. That is because 1 to 0 is 1, this is another 1, there are 3 2's, so in total it's 8. So that's essentially why the first place is 8, so on and so forth. So I think I think we mostly understand the problem, and actually it is most likely a graph. But we can call it a tree, and it's not a binary tree at this moment. So how to solve this problem? So the first idea that comes to my mind is we could of course use some do BFS on top of each of the node, and then we can simply compute the distance between every of the node to all the other nodes. So the runtime is of course is going to be n squared here if we do BFS. So the first naive approach is is to do BFS on top of every node, so the runtime is going to be n squared. So that may not be the best solution. So let's think about some other solutions which could be better than this one. So actually, since it is a tree, what we could do actually here is, well, what we could do is, I think most part, it seems to be, well, what we could do is, well, I think there's some relationship between each of them. So let's see this one. Let's say if there is only one node within the tree, then the distance of course is 0. Let's say there are two nodes. So if there are two nodes, then the distance between the distance to 0 is 1, and the distance to 1 is 1 as well. So let's say there are 3 nodes. So distance to 0 is 2, and then the distance to 1 is 1. Distance to 0 is 2. Distance to 1 is 1 plus 2, and then the distance to 2 is 1 plus 2. Okay. And then let's see if there are, for this kind of thing, I would say, let's say we have a tree something like this. So if we add 2 other nodes here, the distance to node 0 is actually, so original the distance of 1 to 0, which is the same as before, distance 2 to 0, which is the same as before, and we added another 2 things, which is 3 to 0 and 4 to 0. So actually there's some relationship for each of this. So let's say we define 2 arrays. So the first one is the count array. So the count array, so count I means how many, suppose I is the root, how many nodes are there, so under the node I as the root. So it should include the root as well. So like for this one, for 2, we have 3 nodes in this subtree. And for 0, we have 0, 1, we have 0, 1, 2, 3, 4. We have 5 nodes within this tree. And for if root is 1, there is 1 node within the tree. So on and so forth. So let's define another thing. Let's say we have the distance I. So the distance I is all the nodes. The distance is sum of distance for all the children under node I to node I. So like for this one, if we have 2, so we have the subtree. Let's say for the subtree, for this subtree, so the distance is 1 plus 1, which is 2. So this is so under this node there are 2 children, 3 and 4. So the distance from 3 to 2 is 1, 4 to 2 is also 1. So all the children under this root, all the children under this root has a summation of the distance to the root as 2. So if you have this kind of thing, so how to compute the distance to the root of the tree? So essentially that's about, so suppose we are having a root, and we have a couple of the children. So let's say children could be, so we have a couple of the children. So how to compute this for the root? So this for the root, of course, it is, when I say the root, it is like the top root actually. So the distance to the root is actually the sum of the distance children. So we can have a couple children plus the sum of count children. So if we want to compute the distance for this node 0, which is the root, actual root of the entire tree, so we have a couple of the children. So if we compute the distance if we compute this I, which is all the children for the days, so if you have that result ready, so we can compute that. We can based on the computation. We compute the this root is the formula using the summation of all the distance from every of the children. And why we do the summation of all the count of the children? So that is because we need to include this one, which is, so like for example, the distance between 4 to 2 is 1. So the distance between 4 to 0 is 1 plus 1. So that's essentially why we add another summation. We add another summation of the count of the children. So it's essentially we are just one step away for all of the children. We are just one step away from the real root. So after we compute the root, so for this step, what we could do is we could compute using the post-order traversal to compute the this I and count I here. So that will be the first step. The first step is to compute count I and this I. So next part, what we could use post-order traversal. And the next step is step 1. And the next step is to do another traversal here. But instead, this traversal we are going to do a bit different. So this time we are going to do a pre-order traversal about the tree. So essentially we have this root is actually what we are trying to get as the final answer. So like for this, let's say for this tree, after the computation, after the first step, so for this kind of tree, after the first step, we will have this 0 as 8. But for all the others, it's not the same situation. So how are we going to compute this for all the others? The real distance for all the others. So instead, what we are going to do is we could say the real distance. Let's say this is so how to define this? So let's define the real let's say just the result. So result I is going to be what we are going to return finally. So currently we have result 0. So we have this 0 as result 0. So we can leverage this information, and we can also leverage the count I, which is already computed, to finally compute all the results for each of the node within the tree. So how do we do that? So what we are going to do is we are going to do a priority traversal here. So for this one, let's take an example for this one. For this one, we already have the result as the real thing. Well, let me change the tree a little bit. So let's say this is 4 and this is 5. So we already have this one computed, and how do we compute this one? How do we compute the result for node 1? So what we could do is we could use a formula. So the formula would be would be the this for the root. So here it is this 0. So it is going to minus how many numbers are there. So it will be count I plus the number of the nodes. Let's say n, there are n nodes within the tree, minus the count I. So why is that? So still we take this example. We compute the I. We compute the result 1 here. So here we already have the distance to all the nodes. So the distance is actually all the nodes within the left subtree to 0, and all the nodes within the right subtree to 0. So what you could do, so there are actually 2 parts. You can think about this one as 2 parts. So first of all, we need to minus like all the nodes within the subtree to the root. Then we are going to have all the nodes with all the nodes under node 1, the distance to all the nodes under node 1 to 1. And then there is another part, which is the right subtree. So how are we going to compute all the nodes, the distance of all the nodes under the right subtree to 1? So that's essentially we are going to have, so let's say this one we are actually decomposing. So let's say this is the distance. This is the distance for all nodes within left subtree to root, plus distance for all the nodes within right subtree to node. So we decompose this one into 2 parts, and if we just minus the count I, which is so this first part is going to be the distance of all the nodes under the node 1 to node 1, and the second part is actually all the nodes within the right subtree to the node 1. So that's because we just minus the distance from the we just plus the distance. We just add. So remember that all the nodes within the right subtree is just one step away from this node. So we are going to plus the number of the nodes within the right subtree, and also the root itself. So this is the formula how we are going to compute the final results we are going to do. So the whole solution is going to take about all of n to finish, because we just do one post order traversal and on one pre-order traversal. So that's essentially how we solve this problem. So the next part is about to do some coding work. So the next step is about to do some coding. For coding, we care about the correctness and the readability, and also don't be too slow here. So let's do some coding work. First of all, we are going to have the distance as let's think about some first of all let's think about some edge cases. So if n is equal to 1, then we are just going to return 0 for everything, I think, because there's only one node here. So let's say is equal to int n, then you're going to return without doing any further computation. Otherwise, it is our normal calculation. So we are going to define. So first of all, we need to build the graph based on the edge. So we are going to have a map of integer to the set of the integer. So this would be the graph or the tree, so depending on how we call it. So this is a new hash map, or you can just simply define a other helper function, which is to the set of the integer, which is the map get graph. So we have the edges here. So here we have the map integer set of the integer so we are going to store every edge here. So this is the from node is edge 0, and then the to node is the edge. Because it is undirected graph, so we need to add two edges here actually. So we are going to say if the graph doesn't contain the from node, then we are going to graph dot put the from a new hash set, and then graph dot put get from dot add the 2, and similarly we are going to have a edge from to from. So it is going to be graph dot put to a new hash set, and then graph dot get 2 and add the from, and finally we are going to return the graph. So that's the thing. So the graph we're just going to call the helper function, which is get graph on the edges. So the next part is about we do some traversal to compute the count and the distance. So what should we do here? So let's say we just have the counts. And nose, and then we have the distance. Let's say this is also n nose. So we are going to define a helper function, which is post outer traversal. So let's say this is post outer. So post outer, we are going to of course pass in the graph here, which is not from the integer set of the. So this is the graph. So the current node we are trying to see, and also I think we also need to include the previous node we are saying, because we don't. So for example, for this tree we have like 3 edges, to 0 to 3 to 4 to 1. So because we are doing post auto traversal, we just need to we don't really we want to go through every of the children, but we don't want to go back to go through the parents. So that's, so if the node is equal, if the current node is equal to the previous node, which means the current node is equal to, if we try to visit the parent node, then we just skip it. And then the next thing is we are going to, at the same time, we are going to update the count array. We are going to update the distance array. Yeah, so that's pretty much it. So here we are going to call post outer traversal. Here we pass in the graph, we pass in current node. Let's say we start from the root, which has index as 0. So suppose, yeah, so let's just assume 0 is the root node here. So let's say this one is -1. Otherwise we pass in the count, we pass in the distance. So how are we going to do this? We are going to go through every other thing for the current node. So every of the neighbor for the current node. So we are going to say, all right, so this is neighbor of the graph dot get the current thing. So like I said, if the neighbor is a parent, then we are just going to continue. Otherwise, what we are going to do is we are going to call the post outer on top of every of the neighbor. So we are going to pass in this. So the current node is going to be neighbor here, and then the previous node is going to be current. And then we pass in the count, we pass in the distance here. And after this, I think what we are going to do is we should be able to, so after this we should be able to compute, we should be able to have the count for the neighbor. So currently we will have count for current as equal to it should be plus equal to all of the count of the neighbor, or we can call it the child here actually for better understanding. So count all the child, and also for the distance we should have so for the distance it is actually plus equal to the current is plus equal to the distance of the children, all of the children, plus the count of the child. And then finally we should plus the count of the current. Yeah, so what is the underlying so why it is something like that? So after the post outer, we should already compute the distance for the child and the count of the child. So essentially, for example, for this one, we have, for this node we have the 3 children, 3, 4, 5. So after we compute this, we should have the distance for 3, distance for 4, distance for 5. So suppose there are some children under node 3, 4, 5 as well. Then we are going to compute. So the count is essentially like the summation of everything, and then finally we plus 1 because we also need to consider the root node. So for the distance, it is something like all of the children under node 3 is just one step away from 2. So we just need to plus the number of the children under node 3. So that's essentially so that we can compute the distance to the node 4 for all the nodes under node 3. So that's essentially what this piece of code is about. Alright, so after that one, another thing we need to do is we need to do a pre-auto traversal. So pre-auto traversal, so this is pre-order traversal. So in the pre-order traversal, we are going to apply this formula listed here to compute the real distance for the final thing. So why we do pre-order traversals? That is because the top node is already the real thing we are going to finally return. So we are going to, based on this result, we compute the rest of the result from top down order. So we have the integer. We still passing the map here. Still the current node, the previous node, and also the count. And also, let's just reuse the distance here. So we are not going to define another results array. So because essentially we can just reuse this distance array here. So let's do a pre-order traversal. This is a graph. This is from 0, -1. And then we have the count, we have the distance as well. And finally, we are going to return the distance. So pre-order traversal, actually we are going to go through area of the child and apply the formula on top of that. So let me just paste the formula here. Yeah, so let's say n is equal to, let's say num nodes is equal to count.length, which is n here. So this is, let me just replace this one as num nodes. Alright, so for area of the child, so in child, in graph dot get the current stuff. So still, if the child is equal to the previous one, then we are just going to skip it. Otherwise, we are going to say, okay, we are going to, so we are going to say the distance of the child is equal to the distance of the root minus count of the child, and the plus num nodes minus the count. So this is a count of so the count of the child. Okay, so that's essentially how we compute this one. Alright, so distance of the current, which is a root node, minus the child plus num of the nodes. Yeah, I think that's pretty much it. Yeah, so we do a top-down pre-order traversal. Yeah, so I think that should be pretty much it. Let's give it a run and see how it works. So the compile. Okay, so for some typo here. Okay, so another typo. Just rely on this platform to help us to do some debugging. So we have output as 8, 12, 6, 0, 0, 0. So it means that we have some bugs here. So like for this one, let's go through this piece of code and see why we are having some bugs here. So if the children, so let's output the count and the distance actually to see if we are doing something wrong. So is smaller than the count, is smaller than n plus I. So this is I plus the count I, the plus the dis I. So here we have so for node 0 we have 6 of the nodes and distance is 8. 1 we have only 1 and distance is 0. And for 2, we have 4 nodes, distance is 1, 2, 3, it's right. For node 3, 1, 0, 4 is 1, 0, 5 is, I think everything is good here, so which means that our post order is giving us the right thing. So let's see the next part, which is the pre-order traversal. For the pre-order traversal, oh, okay, so actually I forgot to do the right thing here. We should also call this one. So on child node, the current node, and also the count and the distance. So that's essentially why we are not doing the right thing. Okay, so after that we are good to go. So let's do a summation for this one to see how it works. Alright, so everything works here, and that's pretty much about this coding question. So the last step, don't forget to do some testing. So I just rely on this platform to help us debug and do the testing for the simplicity of this video, but depending on the platform you're using, you may need to, if it is not runnable, you need to go through some test cases, explain it manually to the interviewer. So that's pretty much it about this video. If you have any question about the solution or about whatever, feel free to leave some comments below. So if you like this video, please help support the channel. I'll see you next time. Thanks for watching.